Okay, this is the first practice problem from the meeting on Thursday, the 8th of September. The handout says Tuesday, the 8th of September. It's the RC circuit with the voltage driven by the voltage source, a pair of resistors, the same value, 10 k ohm. The capacitance is in parallel with the second resistor. There's several ways you can think about this problem. The voltage source is constant, it's piecewise constant, so it's 12 volts for negative time, and then it's 6 volts for t greater than or equal to 0. 10 k ohm resistors, 2 microfarad capacitor. We want to find the capacitor voltage for all times. So we're going to do this using Laplace, because that's the topic of the unit. And we're going to first find the initial conditions by solving for t less than 0. And there's a little bit of insight you can have here, and that's looking back from the capacitor terminals. If you thought of that as a Thevenin equivalent, you would just see a voltage source of half the strength because of the voltage divider between R1 and R2 being equal. And looking back as the Thevenin resistance, you would see R1 parallel R2. So when we go to do our time, we see our time constant. It ought to be R1 parallel R2 times C, and we can anticipate that. But let's go ahead and derive we'll find the initial condition first. So for t less than 0, everything's been constant. Capacitor acts like an open circuit. We just see the voltage divider. So Vc of t is 6 volts, t less than 0. And then because of the continuity of the capacitor voltage, that has to be the same as the voltage at t equals 0, even though the voltage on the input side changed. So it's got to be 6 volts at t equals 0. So that's our initial condition we'll need when we go do our Laplace. We want to find the differential equation, and I like doing the node method. It's consistent. So if we start at the node where everything comes together, the current leaving to the left through R1 is, of course, the node voltage there is Vc of t, capacitor voltage. So the current leaving through R1 to the left is Vc of t minus Vs of t over R1. The current leaving down is Vc divided by R2. Vc minus 0, and that's why we do the currents leaving, so to get that Vc minus 0, we don't get a minus sign there. And then the current leaving to the right is the capacitor current, which is just C times dVc dt. And those all have to add up to 0, so we can combine terms, put the derivative terms, right? You want to write things in terms of decreasing orders of derivatives. And then we have the Vc term, which has weights 1 over R1 and 1 over R2. And there's our R1 in parallel with R2. So we can call that Req, 1 over Req. The resistance is still in the denominator. Vc of t, and that's got to equal 1 over R1, Vs of t. Dimensionality check, that's a current, Vc over resistance, that's a current, everything agrees dimensionally. So there's the differential equation. We can, traditionally, you don't want to split, you've got coefficients all over the place here. And you either want to put everything loaded up front with a 1, it's a trailing trailing coefficient, or you want to have a leading coefficient of 1. Let's go with the leading coefficient of 1. So dVc dt plus 1 over Req c Vc of t equals 1 over R1c Vs of t. Again, we could have easily multiplied everything through by Req. To have a leading coefficient of 1 here. You get the same answers, but when you work with higher order stuff and you have to factor it, then you have to have a leading coefficient of 1 in the denominator, so may as well go ahead and get there now. Okay, so there's our diffeq. We want to go to the Laplace world now. So the transform of dVc dt is s, Vc of s minus Vc of 0. And then we have plus 1 over Req c times the transform of Vc. And that's got to equal 1 over R1c times the transform of Vs. Again, we combine coefficients of Vc, which in this case, so we have s plus 1 over R EQC, all times VC of S. And then we take everything else to the other side. We keep our 1 over R1C, VS of S, and then we bring VC of 0 over. And now we just have to divide both sides by S plus 1 over R EQC to get the solution that we're looking for. The output in the Laplace domain is 1 over R1C. Okay, and here's just a technique trick. We're going to have all this S plus 1 over R1, REQC stuff in the denominator. We've already got stuff in the denominator, but it's just a number, whereas this is a function of S. So take the number and just call that all the numerator, 1 over R1C. And then you get S plus 1 over REQC in the denominator. Otherwise, you've got this R1C floating around, and you don't know what to make of it, and things like that. Then we have the V, that's all times VS of S, and then we have the VC of 0 term, and it just gets the 1 over S plus 1 over REQC times VC of 0. So that's the expression for the output in the Laplace frequency domain. And now we want to both find the Laplace transform of our input and get our our parameter values, the component values, and plug them in here. So for t greater than 0, greater than or equal to 0, Vs of t is 6 volts. So that means that cap Vs of S is 6 over S volts seconds, but we don't really put the units in when we're doing the Laplace stuff because it just gets in the way. But you can again check, Laplace has dimensions of volts seconds. That's a per second, that's a per second times volts seconds, so that's still volts seconds. And that's volts divided by per second, which is going to be volts seconds. So dimensionally, it's still consistent. We put that into our expression for cap Vc of S. We need the number, I guess we can get our numbers now. So R1 is 10 k ohms times C, which is 2 microfarads. So I'm going to go, so R1 times C is 20 milliseconds, time constant, and so then 1 over R1C is 1 over 20 times 10 to the minus 3, which is going to be, make that smaller, make that bigger, 1/2 of 100 is 50 per second, and then our equivalency is going to be 5 k ohms times 2 microfarads, so it's going to be 10 milliseconds, which is half as many milliseconds as that. So 1 over our equivalency is going to be 100 per second. So let me see, 1 over R1C was 50 over S plus 100, and then we've got 6 over S for our input term, and then over here we have 1 over S plus 100, and Vc of 0 was 6 volts. We have to do partial fractions on the term on the left, so we'll do that by cover up. Cover up S equals, the S equals 0 term, let S equals 0, and what's left? We've got 300 over 100, which is 3 as the coefficient of S, and now we need the coefficient of S plus 100 from the left-hand term. Cover up S plus 100, let S equal minus 100. We've got 300 over minus 100 minus 3, and then we still have this plus 6 over S plus 100 term over here. We'll go ahead and go back to the time domain before we combine these so we can see the different parts of the answer. So Vc of t is 3, 1 minus e to the minus 100t, and then over, that's the zero state response that comes from turning the input on, and you'd get that if the voltage across the capacitor had been equal to 0. And then over here we get 6 e to the minus 100t, which is a zero input response that you would get if the capacitor had been charged up to 6 volts and you just let it go and didn't have any input. But you can put those together and get 3 plus 3 e to the minus 100t. And that's all good for t greater than or equal to 0. The problem asks you to do a case result to write the total answer. So Vc of t equals 6 volts, t less than 0, 3 plus 3 e to the minus 100 t volts, t greater than or equal to 0. And it asks you to draw a graph. So for t less than 0, it's 6 volts. It comes down to 3 volts in the long run. It's going to decay like an exponential. And it's going to have a time constant of 10 milliseconds. And that's the end of the problem.